This is typically denoted with a small p. It's also a function of x, and this is just by definition the derivative of f with respect to x. Okay. And because of this, it is therefore also true that f of x can be written as an integral from whatever lower range is allowed, minus infinity or whatever else, up to x of dx prime dx prime. Okay, this is just a simple mathematical relation, so you can think of this as a definition. Now, why is this definition nice? Because this, if you think of your integral as a summation, it immediately tells you that there is a nice probabilistic interpretation here. This quantity here, this infinitesimal quantity here, px prime dx prime, this is the probability that the variable capital X takes values in the range x prime to x prime plus dx prime. Okay? So therefore, if that is the case, then what is the probability that the variable takes values less than x? Less than x means it can be between minus infinity to minus infinity plus dx prime, then that to that plus dx prime, and then you keep on adding up all these probabilities. These are all mutually exclusive. Either the variable takes a value here or it takes a value there. Okay, so mutually exclusive events add their probabilities. So with the sum over these probabilities, you get the total probability. So there's a nice probabilistic interpretation here. But apart from that, this is just a definition. Okay. Is this familiar? Have people seen this before? Yeah? Okay. Good. So now you have a probability density function for your variable. And okay, so statisticians like to be very precise, and they will distinguish between the random variable itself and the values that it takes. Okay, so for example, it appears here. This is the variable. It takes values less than or equal to x. So you distinguish, you write one with capital letters and one with small letters. We need not be so careful. Sometimes I will just use little x for the variable itself. If there is any confusion, you let me know. Okay, so for now, let's stick to this notation. This is for one variable. Suppose I have two variables, capital X and capital Y. I can go through the same exercise for both of them. X and Y will individually have their cumulative distribution functions. They will individually have their probability density functions. So P of X and P of Y. We may also be interested in the joint distribution of both X and Y. Okay? In this case, you will have something like a joint probability density function, P of X and Y, which you can relate, in terms of the individual cumulative distribution functions and so on. But here it's easier to just keep track of this by saying that this quantity, this infinitesimal quantity, is the probability that x takes values in x to x plus dx, and that y takes value in y to y plus dy. Okay, so this is the joint probability density function. And one very useful thing, one very useful property of or a subset of these kind of joint probability distributions is what happens if x and y are independent variables. That means what you do to x does not affect y and vice versa. So for independent variables, can anyone tell me what I can write, how this simplifies? Dx plus py? Dx into py. Okay, so let's be even careful here. This is some function p sub x of x and some maybe other function p sub y of y. They need not be the same function. Okay. But the point is that for independent variables, the joint PDF splits up into the product of the two variables, the two individual PDFs. And this you would have also seen, I don't know, in high school also when you first studied statistics. If I give you event A and event B, you can ask, are these events mutually exclusive? Are these events independent? If they are mutually exclusive, then the probability of A or B is the probability of A plus the probability of B. And if the events are independent, then the probability of A and B is the probability of A times the probability of B. So this independence is all that you're doing here. It's the same per event in probabilities translated into densities here. The reason it is called a density function, the reason it is a density is because if you look at the definition, this capital F is a probability. So capital F is dimensionless. It's a number between 0 and 1. This P of x is a derivative of capital F with respect to x. Now x can be anything. X can be a length, x can be rabbits, x can be number of planets, okay, not number, but it can be anything, it can have some dimensions. So this quantity has units of 1 over x. So it is a per unit x quantity, and therefore it is a density, because density is something like per unit volume or per unit length. Yeah. So that's why this is a density. Okay, and then one very basic property that if I take any, so now this I can generalize. Yeah. So I don't need to have 2 variables, I can have n variables, and I can talk about their joint probability density functions, P of x1, x2, xn. And then one thing that is always satisfied is that, so for one variable, if I do this integral over the whole range, if I don't write anything, it means I'm taking the integral over the whole range. This is the probability that x takes some value on the real line. So that probability has to be 1, because x is a real valued variable. So this is 1. Similarly, if I integrate a joint distribution, this will also be 1. Can anyone tell me what I would get if I take a joint distribution and I only integrate one of the variables? Sorry, so who you want to say something? Yes?
The distribution for that is single dependence.
Which dependence?
Like px2 x2. That
px2 x2.
If they're independent, I'll get 1.
Function of the other.
Does it matter if they are independent?
No.
Yes, it matters that they are independent. Suppose they are not independent.
Then we cannot take the pfx, we cannot take the differential functions and to put the 2.
But I just want this integral. I don't care whether they are separable or not.
One
Yes, sorry, one at a time there.
Maybe the function of other variable on the.
It will only be a function of the other variable. Which function of the other variable will it be? There was some answer here.
Density function of that. It's just defined as the marginal probability.
Good. So this is just the PDF of the other guy. So you're right. It is a function of the other variable. We in fact know what function. It is the PDF of the other function of the other variable. Yeah, and this does not depend on independence, because what you are doing here, think about this integral, right? Integrals are summations. You are just taking probabilities and adding them up. Which probabilities are you adding up? The probabilities, all the probabilities for x1 to take whatever value. Right? You are not putting any constraint on the value of x1. You are saying let x1 take whatever value it wants to. What is the result of this? What is the resulting probability? That has to be just the probability of x2. And you can also do dimensional analysis on this and make sure that everything is reasonable. Yeah. So on the right hand side, if we have a PDF of only one variable, it should be a density in that variable. So it should have units of per unit x2. Let's see what is on the left hand side. I took a joint PDF, which is a density in 2 variables. So it is per unit x1, per unit x2. But then I integrated it against dx1. So this dx1 with a px1 cancels off those units, and I am left with units of per x2 on the left hand side also. Okay, so everything makes sense. Everyone with me so far? Yeah? Good. Okay. So now that you have PDFs, you can do things with them. In particular, you can take expectation values. So if I have a function, I have some function, let's say g of x. G could be anything, okay? Let's say g of x is x squared, just to be definite. I want to know what is the typical value of this function of my variable. If the variable itself is a random variable with a certain PDF p of x. So that thing is denoted as the expectation value. It's denoted, I mean the notation can be different. Look up Wikipedia, they will always call it capital E. I like to put angular brackets here, they mean the same thing. So as long as I tell you what I'm doing, it should be okay. So what you do is you integrate g of x with weights that are given by the PDF. Okay, so this is a weighted integral. So you are using the probability density to assign weights to the values of g of x. Okay. This is called an expectation value because this tells you on average what to expect. This also has an interpretation if you want to do practical estimates of this, which we will come to in a second. Basically this is like saying I have this g of x takes some value or x takes some value in this universe. Okay, so at this particular time, at this particular place, the temperature in this particular room is 25 degrees centigrade. Now imagine another universe in which there is another room filled with people like you, okay, listening to maybe a slightly different professor. There the temperature would be 25.3 centigrade. Yeah. Over this infinity of universes, the temperature may fluctuate by a certain amount. So this is this ideal calculation where if you have access to a variety of, to an ensemble of universes, what is the typical value of some quantity? Of course, this is not what you want to do in practice. You want to do practical things with practical tools, with your experiments and so on. So there what you do is you argue that instead of having an ensemble of several such realizations of a quantity, I may choose to measure that quantity many times. And I will assume that measuring this quantity at different times is basically the same as taking an ensemble of this quantity. Yeah, so the fact that I measure something now and then come back tomorrow and measure it again does not make a difference. And then I can just treat these measurements as independent draws from the same distribution. So roughly speaking, that is what the expectation value does. As a mathematical definition, this is what it is. Okay, it's an integral of your quantity weighted by the PDF of your variable. Now we can choose different forms for g of x. The simplest form is if I take g of x equal to x, then I get the expectation value of x. Yeah, so this is just integral dx px times x. This thing has a name. It is called the mean of the distribution. So if we're sticking to this notation where the variable is capital X with a distribution d which has a PDF p, then this is the mean of the distribution d. Is this visible from there or should I write it here? Similarly, if I construct this quantity, then this is the same as doing, convince yourself that when I do this and I apply this definition, right, with the angle brackets, what I get is just okay. Convince yourself that these two things are the same. Do it on your own as homework. This is called, what is it called? The variance of D. So I am being careful here. The mean and the variance are properties of the distribution D. Yeah. Loosely speaking, we will also refer to them. You will typically refer to them as the mean and variance of X. But you have to realize that what you are really doing is characterizing the distribution of X. X is a variable. It obeys a certain distribution. That distribution has some properties. These are the properties of that distribution. These are statistical properties of the distribution. Statistical in the sense that they are defined in terms of expectation values. They are not defined in terms of the specific values of the variable that happened to arise in your experiment. Okay, they are defined as statistical quantities. They always involve expectation values. Yeah. So they are fundamental properties of the distribution. So let's give them some notation. So this mean I will usually refer to as mu, and the variance I will refer to as sigma square. It makes sense to call this a square because this is a positive definite quantity, which you can see already from here. X minus average x the whole square is positive definite. P of x is positive definite because it is px dx is always a probability between 0 and 1. Okay, good. So, and you can keep going. Yeah, so you don't have to stop at x. You can do x cubed, x fourth, and so on. And all of these expectation values will give you different properties of your distribution. So so we can append this and say that I have a variable capital X which is drawn from a distribution D, and the distribution is characterized by a bunch of properties. For example, it will have a mean, it may have a variance, it may have other properties. Okay? And all of these are equivalent descriptions. So if I give you the cumulative distribution function and it is a well-behaved CDF, then I can always differentiate it and calculate PDF, P of X. If I have a well-behaved P of X, I can always calculate things like the mean, the variance, etc. by using this formula. Okay? And the set of all such numbers, so there is a theorem which tells you that if you calculate all the powers x to the n and take their expectation value, n going from 1 to infinity, that infinite set of numbers is, knowing that infinite set of numbers is the same as knowing the distribution itself. Okay, these are equivalent things. Yeah. So what we will focus on is just one or two numbers that characterize the distribution, because typically you are not interested. Okay, you may be interested in the shape of the distribution, which we will discuss later, but for now we will stick to things like this. Any questions so far? Okay. Suppose I had a Gaussian distribution. How many other parameters would I need here?
It is standard deviation.
One? None.
None anymore.
You are saying standard deviation. But what is standard deviation?
Positive.
So if you are saying none, then what is standard deviation in terms of?
Sigma.
It is just square root of sigma squared. So that is not an independent number.
Yeah.
So Gaussian is defined as a distribution which is characterized by exactly two such variables, the mean and the variance. In fact, there is a theorem which says that if a distribution is characterized by even one additional parameter than mean and variance, then it must have an infinite number of non-zero additional parameters. Technically, these parameters are called cumulants. Mean and variance are the first two cumulants. So if a distribution has more than two non-zero cumulants, then it must have an infinite number of non-zero cumulants. In other words, the only distribution which can be characterized by a finite number of cumulants is the Gaussian, and that finite number is 2. Okay? But anyway, so in general, you need not have Gaussian distributions. You have a data set, it has some distribution, you don't know it. So it will be characterized by a bunch of variables. So now let us come to the point of today's lecture. Let's say that you have a set of measurements, a set of data points, di, and let's say we know that the di's, each di has been drawn from some distribution d. So each di is drawn from a distribution d, and this is the same distribution for all the n di's. So it's like you've repeated an experiment n number of times. So you don't know what the shape of this distribution is, but you know that whatever it is the same distribution for all of them. And let us assume, okay, so then this distribution, let us say, is parameterized by its mean, its variance, and maybe other parameters. Let us also assume that these draws are independent of each other. Okay, this is what one typically assumes in the lab. You take a resistance, you pass some current through it, put a voltmeter, measure the voltage. Right? Then you pass the current again, you measure the voltage again, and maybe because of the fluctuations or maybe because you look somewhere else, etc., the voltage is a little bit different. So the point is you do this 10 times and then take the average voltage, and that is your best estimate for the voltage. Okay. So the idea is that every time you do the experiment you make an error, but the error that you are making is independent of what you did before. Hopefully you are not making the same error again and again. Okay. So that is what we will assume here, that these di's are drawn from some distribution which has some mean mu, some variance sigma squared. We don't know what the mean and variance are, we would like to know, and these draws are done independently. So we would like to use, we want to use these n measurements to estimate the parameters mu and sigma squared. You could also want to estimate higher order parameters, but we'll focus on mu and sigma squared. Okay, so what would you like from these estimators? So one thing you would like is that these estimators should not be biased. As in, whatever you do to these DIs and you come up with a number which you are saying is my best guess for the quantity mu, this best guess should be unbiased. Unbiased in the sense that if I repeated this particular experiment of n data points many times, right? So you take n data points, you take n data points, everybody in the room takes n data points, and you apply a particular formula to these n data points to come up with mu. So let's say there are 50 people in the room, there will be 50 estimates of mu. If I take the average of those 50 estimates of mu, I should get something that is statistically approaching the actual underlying value of mu. Okay, so in the limit of a very large number of such experiments, whatever I do to these n data points should approach the true value of mu. So it's useful at this stage to distinguish between the true value of mu, which is mu, and what we estimate to be the value of mu. So one useful way of doing this is whenever I have an estimator, so an estimator of some parameter A will be denoted by a hat. Okay, so what I want in this case is estimators mu hat and sigma squared hat. So we want these. Okay, so let's make this a little bit more formal. Let's do the naivest possible thing, right? So let's say my mu hat is just the sum. So I'll take 1 over n times the sum of the DIs. This is what I would typically do to take an average. This is called the arithmetic mean. Yeah? So let's do this. And now what does it mean to ask the question, is mu hat unbiased? So is mu hat unbiased? So the way to answer this question is to ask what is the expectation value of mu hat. Why does it make sense to write something like this? So notice that your DIs are realizations of some distribution. They are draws from some distribution D. So every time you drew a number, it's a sample of a random number. Okay, so the set DI is a stochastic thing in the sense that the set that you get will not be the same as the set that you get. There will be stochastic fluctuations. The fluctuations will be determined by the properties of the distribution D. So if I want to talk about statistical properties of the DIs, I need to take expectation values. Yeah, that is what we said in the beginning. Statistical properties are related to expectation values. So why am I taking expectation value of mu hat? Well, mu hat is a function of DI. So you take your 10 DIs, n number of DIs, and you give them to me, and I will construct this number. And then someone else does the same thing, I will also construct the number, I will get some other way, I will get some other value. Okay, so mu hat is also a stochastic quantity. So I would like to understand the statistical properties of mu hat. And that is the thing that we want to do today. Okay, so I want to take an expectation value of this. So now think about what this expectation value is. So expectation value means integral over the PDF of some variables. Which variable should I integrate over when I take this expectation value? Which is the underlying variables that I am integrating over?
The DIs.
The DIs, exactly. So I have a joint distribution of the n DIs. Okay, so what this means is that I have P of D1, D2 up to Dn, dd1 up to ddn. This is my joint PDF. Now I am taking a function of these variables, which I am calling mu hat of d1, d2 up to dn, and I am integrating this. That is what this expectation value means. Okay, so formally speaking, it is this huge thing. Okay, now let's do some manipulation and see how this thing simplifies. It turns out to be extremely simple. It looks very intimidating, but it will turn out to be very simple. Okay, so first let's say what we know about this joint distribution. What have we assumed about this data set that we can use here? Any guesses? Independence, exactly. So you can immediately say that this thing is going to split up into something like DD1, PD1, DD2, PD2 and so on. So I might as well write it as a product over 1 to n of DDI, PDI. Okay, so now it has simplified to this. And what about mu hat? Mu hat is just this quantity. So it is summation, so it's 1 by n. 1 by n doesn't matter, it's a constant, we'll just go out of the integral. And this is summation j equals 1 to n of dj. Okay? Now let's stare at this for a second. So this is a sum. So this is d1 plus d2 plus d3 up to dn. And here I am integrating over all of them. So I can think of this as integrating over all of them multiplied with a d1 plus integrating over all of them multiplied with a d2 plus and so on up to dn. So I can interchange the order of this product and the summation here, right? Because that is exactly what the summation is. So this is equal to 1 by n summation j equals 1 to n. Inside I have this product I equals 1 to n integral ddi pdi. This product is sitting on its own and then it multiplies dj. Maybe I should write this again somewhere. So what I am saying is that my expectation value of mu hat is a sum. There is a 1 over n and there is a sum of this product I equals 1 to n ddi pdi, and I close this guy and then I have a dj. Now this sum is happening on its own, so let's pick sum j. Let's pick j equal to 1. What do I get for j equal to 1? I have d1 here and none of the other d's appears. So inside here, so let's say I'll write this out explicitly. Okay. So now I'm writing the j equal to 1 term here. So at j equal to 1, I have a product over all of them. So I have dd1, pd1, and then I have the d1 coming from here because it's j equal to 1. Then I have integral dd2, pd2 times nothing, times 1. Then integral dd3, pd3, and so on. And then ddn, pdn. Okay, so this is the first term, the j equal to 1 term. Then I do the j equal to 2 term. What will I get? I'll get this integral on its own, there will be nothing here. Then here, instead of just this much, I'll have a d2. And then the others will have nothing. And so on, d3, d4 up to dn. So what that means is, every time I have only one term which is non-trivial, and all the other terms, what are they? They're all ones, right? So this thing, so I have plus dot dot dot. So this thing is just 1 over n times what? It's a summation of n such terms. So it's a sum j equals 1 to n. Of what? Of integral d dj p dj dj times 1 times 1 times 1 n minus 1 times. So it's just this much. What is this? This is just 1 by n times summation j equals 1 to n of the expectation value of dj by the definition of expectation value. Yeah? And what is the expectation? So firstly, let's stare at this for a second. So what did we do? We took mu hat, expectation value, where the expectation value here was an integral over n variables. And actually all you did was so just think of this is equal to this, right? So this is, in other words, expectation value of 1 by n summation j equals 1 to n of dj. This is an expectation value over n variables, exchange the summation for the expectation value formally, and inside my expectation value is now only over one variable at a time. Okay, so this is a considerable simplification, and actually you might think that this happened because of assuming independence. Go home and prove that this doesn't care about independence. Okay, even if my DJs are all complicatedly correlated with each other, this final result is still true. This is actually always equal to the expectation value of this object. This is just a statement about the linearity of probability. Probabilities add in a very simple way. Okay, so this is always true. So that's why this intimidating looking thing is not so intimidating at the end. It is just equal to this object. And this object is also not very difficult, right? Because what did we assume about the DJs? That they are all drawn from some underlying distribution D, whose expectation value is what? Is mu. And they all have the same distribution, so they all have the same expectation value also. Okay? So this thing is just 1 over n times summation j equals 1 to n of mu. But mu is a constant. So it comes out, I have summation j equal to 1 to n of 1, which is just n. That n cancels with this guy and I get mu. Okay? So what did we prove? We took this estimator, mu hat, which was a naive estimator that we would have taken in school also, and we put angle brackets around it, and we asked what does this equal? And it turns out to equal exactly the mean of the underlying distribution. So that means this is a nice estimator. This is an unbiased estimator. If I take a formal expectation value of this estimator, I get the quantity that I want. That is what it means to be unbiased. Okay, so therefore, so mu hat is unbiased. Good. Any questions? This algebra is okay? Yeah?
Shouldn't unbiased mean symmetric?
Symmetric. What does symmetric mean?
The distribution is, if it's symmetric about the mean, then it...
No, I just want to know is mu hat unbiased. So in this context, the definition of unbiased is whether or not the expectation value of mu hat is equal to mu.
You have defined it that way.
Yes, this is the definition which is most useful in studies like the ones that I am talking about. What you are talking about is an asymmetry of the distribution. But there is no need to introduce a concept of bias there. Bias has a pejorative meaning, right? Bias is bad. If you have a bias, it is bad. But who says that an asymmetric distribution is bad? It's an asymmetric distribution. But having mu hat expectation value not equal to mu is bad, because it means that whatever you are constructing is going to mislead you, right? So it is in that sense that the word bias is used here. Okay.
So,
yeah.
So the final statement that mu hat is mu. So
Mu hat expectation value is mu. Mu hat is not mu.
Okay. Mu hat expectation value is mu.
Yes.
So does this mean that suppose I have a distribution, I make n copies of the distribution, and then I take one value from each of the n copies, and then calculate the mean?
I don't understand what n copies of a distribution means. There is a distribution.
And
So now-
n such distribution, same distribution.
So no, then there are not n such distributions. There is only one distribution.
So we're talking about n experiments.
No, but then the experiments give you some numbers. So those are realizations. Those are samples from the distribution. So let us distinguish between the distribution. The distribution is a function that looks, the PDF of a distribution is something that looks like that. It always looks like this. It is independent of time. It's always been there. It's always looks like this. Now you come and do an experiment. What you will get is a number that sits here. I will do another experiment. I'll get the number that sits here. I guess this is what you're talking about.
Yeah.
This set of numbers. So this is a sample from the distribution. Yes. Okay.
So that's what I'm saying, that if I do the experiment on one apparatus and take say n readings, and I have such apparatus and take one reading from each apparatus, what this equation says is that the mean found from these two should be the same.
Statistically, it should be the same.
It
It may not always be the same,
But
because there will
statistically it
always
should
be
be-
fluctuations.
Okay.
If you have a really large number of apparati, and if you have a really large number of measurements from a single apparatus, you take separately the average of this over the apparatuses and over the single apparatus. These numbers will approach each other. That is the statement. The statement is not that if I take 10 measurements from 10 experiments, or if I take 10 measurements from the same apparatus and I average over this 10 and this 10, these two numbers need not be the same. Okay, if I change that 10 to 100, those two numbers will probably be closer to each other, but it's always a probabilistic statement. So in fact, that good that you brought this up, because that brings us to the next topic, which is what is the scatter of these measurements. So right now we have taken the mean value of these measurements. We'd also like to understand what is the scatter around this mean value. Okay. So in other words, we want to know more than just the mean. We had D of mu. We also want to understand what is sigma squared. This will characterize the scatter in the distribution. Was there something else?
Sir, shouldn't be the expectation of mu equals
Louder.
shouldn't be the expectation of mu equals the mu for the limit of large numbers, like
It need not be. So we will next study a case where I have a parameter for which I construct an estimator whose expectation value is not equal to the parameter, although the estimator seemed reasonable. I will give you an example. It need not always be the case. Okay, in fact that is exactly what we are going to do next. Okay, so we were very successful in taking the DIs and constructing a simple arithmetic mean and calling it an estimator of the underlying mean of the distribution. So let's ask whether that same success carries over into an estimator of sigma squared. Sigma squared is the variance. Remember that the variance is defined as expectation value of x squared minus x the whole squared, or expectation value of x minus x the whole square. Is it obvious to you that these two are the same or not? Just open it out, right? Expectation, so this thing under the expectation value sign I will have x squared minus 2x times average x plus average x the whole square. Okay? Average x the whole squared is a constant number. It's not a stochastic quantity. So average of average x the whole squared is just average x the whole square, it's just itself. Okay. Similarly, I will have a minus 2 times x times average x, expectation value of this. In this, the minus 2 and the expectation value of x are just constant numbers. The only stochastic quantity is this. So this will become minus 2 times expectation value of x, that's this, and this becomes expectation value of x. So this becomes minus 2 times expectation value of x the whole square. So this minus 2 will add to this guy and give you a minus 1, and then you'll be left with the other x squared. So these two are the same thing. Okay? Good. So this is the formal definition of the variance. And earlier, and for corresponding, let's write it down, for mu it's just this. And we said that given our data set DI, it made sense. We proved that it made sense to say that mu hat is just 1 by n summation di. Okay? So maybe it also makes sense to do something similar for sigma squared. So let's try sigma squared hat is equal to 1 by n times summation of di minus mu hat the whole square. Because mu hat, what I'm doing is every time I see expectation value sign, I replace it by 1 over n times summation over I. Okay, that was the trick that worked in the previous case, so I want to use it now also. So if I just do that, I will get this. Now let's ask what are the properties of this object. Okay, so let's take, what do? You take the expectation value of sigma hat squared. So let's do that. So now you have to be a bit careful. Okay, so let's do this. So the 1 over n is fine, summation is fine. Let's open this guy out. So remember, I'm going to pull that trick, right? So this expectation value, I will now not worry about expectation value being over n variables or one variable. I know that whenever I want, I can exchange the expectation value with the summation. And as soon as an expectation value comes inside the summation, it becomes an expectation value over one variable. Okay, one variable at a time. We proved this in the previous case. Okay, so I will pull the expectation value inside. So what I want is this di minus mu hat the whole square expectation value. This is also a bit tricky because there is one piece here which depends only on the particular I that I am talking about. I carry through the calculation. So let's just keep going with this. So this thing I will do. So far everything was straightforward. Now let me first open out the brackets inside, right? The square. So I have expectation value of di squared minus 2 di times mu hat plus mu hat square. Okay. This thing, now slowly you have to start becoming more and more careful. So let's put some brackets. So the first term is okay. It's just expectation value of di squared. There's nothing else to worry about. There's only one I, and it's just di, that I whole squared. I take expectation value. The second thing, this 2 is fine, minus 2, doesn't worry about expectation values. But now, both di and mu hat are stochastic quantities. Di is di, it is a stochastic quantity. Mu hat depends on all the di's. It is 1 over n summation dj. So this thing I have to be careful. So let's leave it as it is for the time being. And for the same reason, mu hat squared is also a non-trivial quantity. Okay. So how do you proceed? Can someone guess? Now what is the next logical step to do, just to help in simplifying the calculation?
B plus mu hat with summation 1 by n.
Exactly. Okay. So because we understand the distribution of D, so let's just replace mu hat with what we know in terms of D. So let's just quickly do that. This is 1 to n summation di squared minus 2 times expectation value of di times 1 by n summation j dj. This is my mu. Okay. That is this term, and then plus I have a mu hat times a mu hat. Both the mu hats are 1 by n summation over the d's. So I have to be careful about how I place the indices. So I have two 1 over n's, so that's a 1 over n squared. Then I have a sum over, I have two summations, so I take a product of two summations. So let's say first one has variable I, second one has variable j, unrestricted sums from 1 to n, expectation value di dj. Okay, and I close the bracket. All good? Okay, and here also let's simplify a little bit. So, so this di, summation, etc. I can always play around. So I can always write this thing as minus 2 over n summation j, expectation value of di dj. Okay, I pulled the summation out of the expectation value as before. Okay. So what you see here is that if you, the basic unit now that you need to understand is this expectation value of di times dj. Okay. So what is this quantity? What is this? Is it 0? What should I use? What result should I use? Independence. What does independence tell me?
Else you can pull the product out of it.
I can pull the product out. So what I can do is, I should be able to write this as di dj. Is this correct? So this is true for all I and j. What happens if I is equal to j? So okay, so people are saying this is okay. So I will say let's put I equal to j. Then I have expectation value of di squared, and you are claiming that that is equal to expectation value of di the whole squared. That is obviously not the case because there is a sigma squared in the problem. Okay. So I need to account for that guy. I need to account for the. So this is always true if I is not equal to j, and then I have independent variables. But if I is equal to j, it's the same variable, so there is no question of independence. It is equal to itself. So this thing has to have a sigma squared delta ij, because then I will have this plus sigma squared, which is the definition of sigma squared. Okay, so this makes sense. Okay. So di dj is this object, and this thing, expectation value of di times expectation value of dj, this is just mu times mu, because expectation value of each di is equal to mu. So this is just mu squared. this is also just mu squared. Is this clear, everyone? Any confusion? This is the trickiest part of the calculation. Okay, so let me just repeat it once. What we did here is to say that di dj, expectation value, I should split into two cases because I am allowing I and j to be whatever they want. So if I is not equal to j, I am talking about two different variables. We assume they are independent. So the expectation, this product of the expectation value of the product becomes the product of the expectation values. So I will have a term that is just mu square. Then I also have to account for the case when I is equal to j. So when I is equal to j, I need to also account for the variance of di itself. So I add that term. Okay. So that's all I did. And by doing this delta ij, now I am sure that for whatever ij I talk about, I will get the correct answer. When I is equal to j, I will have this term. I not equal to j, I will not have this term. Good. So let's use this and simplify the result. So what do we have? So we have expectation value of sigma squared hat. There is a 1 over n out front. Then I have a sum. Then inside what do I have? So first I have di squared. We just worked it out. It's mu squared plus sigma squared. What is next? I have minus 2 over n summation over j of this object. And then the last term is 1 over n squared summation over both I and j of the same object. Okay. Also point out if I make mistakes, okay, because it's not that I will get everything when miss factors of 2 or the sign or something. Okay, so this looks okay. So let's do this. Sum 1 to n. Let's simplify the square brackets first. So this is as it is. Now here, the first term here is a constant. So this summation j equal to 1 to n times this object will just become a factor of n, which will cancel this guy. So I will get minus 2 mu squared. Then this 1 over n meets and summation j meets this guy. Summation over j from 1 to n of delta ij is just 1. Okay. So I will just get minus 2 sigma squared by n. Then let's come here. So 1 over n squared summation ij. Summation ij multiplying a constant will give me n squared. So that n squared will cancel this n squared. So I will get a plus mu squared. And summation ij multiplying delta ij. So the summation j multiplying delta ij will give me 1. And then summation I multiplying 1 will give me n. And that n will cancel one of the n's from here. Okay, so I will get plus 1 by n squared. So sigma squared by n squared. All of this okay? N. Thank you. Okay, so let's simplify. So I have mu squared goes away, which is good because remember what I want is an estimator of sigma squared. So I better not have any dependence on mu squared. So at least as far as that is concerned, we are doing okay. All the remaining terms depend on sigma squared and they depend linearly on sigma squared. So everything is still okay. But what do you get? So I get sigma squared minus 2 over n and a plus 1 over n. So this minus 2 plus 1 becomes a 1. So let's simplify this. This sigma squared over n times summation 1 to n of what? I have a 1 minus 1 over n. Okay. So the summation multiplying 1 gives me an n. Again here it gives me an n. So this whole thing becomes n minus 1. So I get sigma squared by n into n minus 1. So there is something wrong. Okay, this is not sigma squared, right? So that is the answer to your question. Here is an estimator. Everything looked reasonable, right? We took a reasonable expectation value, reasonable proxy for an expectation value, but the statistical properties of this proxy are not very nice. In the limit of large n, you can say, okay, this approach is 1, so it's fine, but it is not 1. It is n minus 1 divided by n. Okay. So how do you rectify this? Any guesses?
This is correct for the factor. Just correction for the factor.
Just correct for the factor, exactly. Everything, all other properties are okay, right? It's linear in sigma squared, it doesn't depend on mu. It is a quadratic estimator which you expect out of any variance estimator. So all that is going wrong is this prefactor, n minus 1 over n. So where I have a 1 over n, I should replace it with 1 over n minus 1, and then that's it, that will take care of everything. Okay? So, or you can do it systematically. You say that I had an estimator. I initially wrote my estimator as 1 over n times summation over whatever. And this thing was okay, this part is fine. But this 1 over n, let me replace it with some alpha. Okay, and I don't know what alpha is. I will set alpha such that my estimator is unbiased. So at the end of the calculation, I will demand that expectation value of sigma n squared is equal to sigma squared. And that will set alpha for me, and in fact it will turn out to be just 1 over n minus 1. Okay? So if you do this, you will find that you have an unbiased estimator. So let me just write that down. So dj minus mu hat squared is unbiased. Is this part clear? Because I didn't explicitly do this, but I hope the argument is clear. Yeah, why I should not have an n there. Okay, we should already start ringing bells about the n minus 1 that I was mentioning in the beginning. Yeah, so this, when I first did this calculation, I was very happy because it answers long-standing questions. This is not the thing that you usually work with in the lab, because in the lab, typically you are not really interested in the distribution D. What you care about is mu, and how accurately have you measured mu. Okay, so what we have talked about so far is to construct unbiased estimators of the first two cumulants of a distribution, mu and sigma squared, using a data set drawn from this distribution. What is more useful is to know how accurately you have estimated these numbers. Because just having a number, this your physics professor must have drummed into you. You cannot just report a number. You have to report a number and an error. So what is your error on the estimate of mu? What is your error on the estimate of sigma squared? Okay. These are also important questions. So what I will talk about is the error on the estimate of mu. And the same logic goes through for error on estimate of sigma squared, but that requires higher order cumulants, so that I don't want to go into today. So the next thing that we want to understand is error on estimator of mu hat. Whatever I am saying, the formal aspects of whatever I am saying carry through unchanged for any other estimator of any other quantity. Yeah? It's only the actual calculations the values that you get here that will change. Okay. So what does this even mean? What do you mean when you want an estimator of the, when you want the error on an estimator? So go back to what this estimator is statistically. It is a random number which you have constructed out of other random numbers. But the reason to construct this particular random number is because it has some nice information in it. It gives you information about some nice quantity that is defining the distribution, okay, or defining your measurement or whatever. So what is going wrong is that every time you repeat the experiment, you will not get the same value for this estimator. Every time you do the experiment, you will get a slightly different value. So this estimator is a random variable which has its own distribution. We just saw that the expectation value of this distribution is the same as the expectation value of the underlying distribution. That is how we constructed this estimator. But this variable mu hat, it not only has an expectation value, it also has a variance. And a third moment and a fourth moment and all kinds of other moments. Whatever you could say about a distribution, any distribution D, you can say about mu hat also. Mu hat has its own distribution. So what we would like to understand is what is the width of this distribution. Because a nice estimator will be something whose expectation value is what you want, which you've got, you've constructed it, but which also has a very narrow width. So that if you repeat the experiment a few times, you will not get something very far from the truth. Okay, so within a few times you will be able to say with confidence that the underlying expectation value of your original distribution is something. So we would like to estimate this width, which is the variance of this quantity. You always go back to the Gaussian if you get confused. So we have so let's say 0 is here. I have some non-zero mu and I have some width. Okay, I want to estimate this thing. This sigma squared is not this sigma squared, so let's call it differently. So let's say sigma squared mu is defined as the variance of mu. Okay, this is the error on mu. So this sigma squared mu need not be equal to the original sigma squared. It may not even be related. You don't know what it is right now, but we would like to know what it is because that tells us what the error is. So I will do this in the next 5 minutes or so, and then we can stop for the day. We already derived most of the results that we need to calculate this quantity. So this is super straightforward. Expectation value of mu hat, the whole square. The expectation value of mu hat is mu, so this is just mu squared. So you never have to worry about it. Okay. So sigma squared mu. So let's just write sigma squared mu plus this object. This is mu squared hat. Sorry. Mu hat squared expectation value. This is what we really are interested in. So what is this? Use the same tricks as before. Before I take the expectation value, mu hat itself is 1 over n summation, and I have two of them. So I have 1 over n squared. I'm going to skip steps now. I already pulled out the summation from here. I have di dj. Okay, this is our old friend di dj. Let's replace it. This is 1 over n squared times mu squared plus sigma squared delta ij. Okay, so this thing sigma ij times mu squared will give me an n squared, which will cancel this guy. So this will be mu squared, and this will be plus sigma squared times n divided by n squared. So this divided by n, and this is equal to this plus this guy. So sigma squared mu plus mu squared is equal to this. So I cancel and I get that sigma squared mu is sigma squared divided by n, or sigma mu, which is the standard error on the mean, is sigma divided by root n. Okay. So you see something. Okay, intuitively everything makes sense. This variance of the estimator is related to the underlying variance, which makes sense. Why? Because if there were no underlying variance, if the underlying distribution were very tight, very narrow, then whenever you take 10 realizations, n realizations of that distribution, you will always get the same number almost. So if you take an average of that, you will again get the same number. So you should not have any width in mu hat either. Okay, so the fact that it scales with sigma squared is sensible. What is also nice is that it scales with n. This is the standard thing, that if you take many measurements, compared to 10 measurements, 100 measurements are better, because the error will go down by a factor of square root of n. Okay, so the square root n scaling comes out from here. And yeah, this is basically all I wanted to say. So there is some technical jargon again here which is worth keeping in mind. So this sigma mu is called the standard error on the mean. And sigma, which is, remember, a property of the underlying distribution, this somebody had mentioned before, this is called the standard deviation. It is also equal to square root of the variance. So I am being careful to distinguish between properties of the underlying distribution and properties of the estimator. Okay, so for the underlying distribution, there is an underlying mean and an underlying variance. The square root of that variance, sigma, is called the standard deviation. So this mean and variance or standard deviation, these are properties of the underlying distribution. Then you make measurements. you have a set of n measurements, di, from which you construct estimators, sigma mu and the underlying standard deviation. But imagine doing an experiment. All you have is these numbers, di. Okay, so if I want to construct an estimator of mu, I know how to do it. I just do 1 over n summation di. But how do I report the error? I don't know the value of sigma. Okay, because nobody told me the value of sigma. All I have are these numbers di. Well, we just worked out an unbiased estimator of sigma also. No? So an unbiased estimator, so if I want to report mu hat and sigma mu, in practice, mu hat is just the usual mu hat, but sigma mu, what you can always do is report 1 by root n times the square root of your estimator of sigma squared, the one that we derived earlier, which means this becomes square root of summation over j dj minus mu hat the whole square divided by n times n minus 1. Okay. This is the standard error formula that is routinely used, and this is why one uses it. Okay. Any questions?
What is an estimator for sigma mu?
You want an estimator for, so this is an estimator for sigma mu. Exactly. It is an unbiased estimator for sigma mu. But it may not be unbiased. Actually, that has to be checked.
Because the square root is...
Exactly. But that will lead you into an infinite loop. You see, you will keep...
So you could say that sigma hat squared by n is an unbiased estimator for sigma mu squared.
So, what is usually, so what I want to do here is to give you a reason for the practical estimator that you use. The reason is this, that in the limit of small number statistics, this object will give you a better estimate of the standard error than just replacing this with a n here. Okay? That is the only point. And the main role of sigma mu is to tell you about the width of your estimator. So as long as you have a reasonably accurate width, you're okay. Of course, you can try to make it more accurate. As homework, you can try to work out what is the error on sigma squared hat. What is the variance of sigma squared hat? We know that the expectation value of sigma squared hat is sigma squared. We constructed it like that. What is the variance of sigma squared hat? So people who enjoy doing these expectation value calculations, you can spend the evening doing this. Okay. Any other questions? Yeah?
So we here we don't know the bar. Like we know that as we are increasing n, so my sigma mu is decreasing, and the closer my mu hat is to mu. And
in a statistical sense.
In a statistical sense.
That's right.
And mu is what nature is giving me.
That's right.
So that's why we are calling sigma mu to be the error of my mu hat.
Yes.
It has nothing to do with like something.
Well, sigma mu is the error on mu hat. It has a nice scaling also. By construction, the more the number of experiments that you do, the better your estimate of mu hat, of mu. That's right. So what is the question?
So like here, my question basically was, why are we calling this an error? Like how does this quantitatively give me the error of mu hat?
Because it gives you the uncertainty in mu as characterized by the width of the distribution of mu hat. Gives you the uncertainty in your estimate of mu. Nature has a value of mu. That is something. Okay, you want to know what that value is. You will know that value within some statistical uncertainty. That uncertainty is given by this one thing. So it's a very quantitative measure of uncertainty. Anything else?
Can we get the skewness of the curves from these data?
Yes, yes.
Positive
Figure out what is an unbiased estimator for skewness. So you need to know what is the definition of skewness in terms of formal expectation values. Then repeat what we did.
Okay.
Do the naive thing and say I will replace all expectation values with 1 over n summation over j.
Okay.
Right? And inside wherever I see something like x squared, I will replace it with dj squared or dj cubed in this case. And then ask what you get. You will get something. You take the expectation value of that object. Is that equal to the actual skewness?
Okay.
Defined in the formally correct way. Right? And then what do you need to do to correct it? So an excellent place to read all this is numerical recipes. It's a numerical, so it's a coding book but it has one full chapter on statistics and data. I think 2 full chapters on this. Okay, so that is warmly recommended. Alright, so let's stop here and we'll meet tomorrow morning.